Good morning, everyone. So let's get started. In the last couple of classes, we studied the distributed lossless compression problem, where you have two correlated sources, basically two files, which are correlated with respect to each other, and they're distributed according to some known IID distribution Pxy. And the goal was to compress them independently, but then decompress them jointly at the receiver. And we saw that if we want to look at the best possible rates or the minimum rate of compression for these problems, then the rates can actually be below the individual optimal rates. So the rate for user one can be less than the entropy of user one, and the rate for user 2 can be strictly less than the entropy of user 2. In particular, we looked at the achievable rate region, which is the set of all rate pairs which can be achieved. That is, for which we can construct encoders and decoders such that for a sufficiently large n, the probability of error is arbitrarily small, and the rates are arbitrarily close to R1 and R2. Right. So and we had both inner we derived both upper and lower bounds, or so-called inner and outer bounds for this problem. So an inner bound is basically an achievability result, an outer bound is basically a converse result. Right. And in the last class we studied the achievability proof for this particular problem. And in particular, we showed that by using random codes, one can achieve every point in this blue region over here. Right. So this result was first proved by Slepian and Wolf, and that is why it is called the Slepian-Wolf theorem. All right. So in this class, we'll see some extensions of this problem, as well as some more aspects into the encoding and decoding part, how we can make encoding more efficient, encoding and decoding more efficient for certain sources. And then we'll switch gears and talk about compression, but lossy compression. So far, we've looked at fixed length lossless compression with vanishingly small probability of error. So we'll have a very brief discussion about lossy compression and the techniques involved over there. And once we're done with lossy compression, we'll move back into channel coding. So from the next class, sometime in the next week onwards, we'll start looking at multiple access channels, which is the first multi-user communication problem that we'll be looking at. So the tools that we use over here will again be used for some of the tools that are used over here, such as joint typicality and conditional typicality and so on, will again appear when we talk about multiple access channels. All right. So before we proceed, are there any questions?
Yes, sir. Am I audible, sir? Hello?
Yes, you're on.
So, sir, in the beginning of the lecture yesterday, so we said that in a distributed lossless source coding problem, like R1 less than h of x and R2 less of h of y, it cannot be achieved, right, for p equal to 0 and allow variable length compression.
Exactly. So that is for zero error compression, zero error variable length compression.
Okay.
But now what we're looking at, what we've been talking about, is fixed length compression with a vanishingly small probability of error.
Okay, so for
Right?
so the problem posted in Piazza, it is related to like for
Yes.
fixed length compression.
Yes.
Okay, sir.
Yeah.
And the second question, sir, in the R1, R2 plot, like the current plot which is being shown on the screen. So the region, the red colored triangle, as in greater than h of y given x and h of x given y, but less than h of x and this h of y. So that red color, the triangular region.
So you're talking about this region over here.
Yes. Yes,
Yes.
sir. So that should be achievable, right? For h of y given x greater and h of x given y greater.
No. So the optimal rate region is the intersection of all these three regions.
Acha, intersection. Okay,
Right?
okay.
So a rate pair which satisfies all of these three constraints is achievable.
Okay, we have to consider intersection in this.
Yes.
Okay, I thought
And
or condition for
no,
this.
no,
Okay.
no, 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 no. So all of
Okay.
this is and.
Sure, sure,
Okay,
sir. So,
that's a good point. But yeah, so all these three constraints have to be satisfied. So only if all of these three are satisfied, we can have vanishingly small probability of error. We can construct encoders, decoders with vanishingly small probability of error.
okay, okay, sure, sir.
All right. So basically, the non-achievable region is the union of the three regions: R1 less than h of x given y, R2 less than h of y given x, and R1 plus R2 less than h of x plus h of xy.
Yes, sir.
Okay. All right. So any other questions? Okay, so one of the questions that was raised last time was regarding the complexity of encoding and decoding. So recall that the way the encoder worked was that it had this table of so both encoders maintained separate tables, which basically correspond which basically tells for each sequence which code word or which compressed file needs to be transmitted, right? And what does the decoder do? The decoder has another table, which contains, of course, it contains these two tables, which tells it which sequences map to a particular code word, and it also has a separate table consisting of all jointly typical sequences. So if you have a particular pair which is not in this table, or if you have two particular sequences which have the same code words but are also jointly typical, then you declare an error. Right? But note that there are exponentially many sequences. So in fact, the size of each of these tables is exponentially in n. Right? And for even reasonably moderate n, which is maybe 10,000 or so, this can be very, very large. So obviously, this is not a practical scheme. Although it tells us that this proof tells us that we can achieve a particular rate, it tells us what the best rates achievable are. It is not. It can't be implemented in practice, right? And so one approach is can be which is used for uh, for specific sources, such as the discrete the source that we looked at in a previous class, the doubly symmetric binary source, is the following. So for certain sources, such as this one, we can construct a different set of encoders and decoders, which also get you to the same rates. Okay. Uh, so let's look at that. So once again, the problem is the following. We have two users and we want to compress two files or two sources independently, but we are allowed to do joint decompression. All right, and the goal is to still achieve maybe a point in the Slepian-Wolf rate region, or the rate region or the blue region that we had previously, but now we want to make sure that the encoders and decoders are as efficient as possible. Okay. So one approach, I'll only sketch the approach and maybe give the details as a homework. One approach that people commonly use for compression is the following. So, so we use what is called a linear code. If you've seen what a linear code is in channel coding, that's fine. If not, it doesn't matter. Or it is just a matrix, right? Uh, so so one approach to reduce complexity is the following. So use linear codes. And the way this works is the following. So the encoding of each xn or yn is obtained by multiplying by some matrix. Okay, so the compressed file is going to be obtained by, so note that xn and yn are now binary. So this works for the doubly symmetric binary source, wherein x comma y, so x is Bernoulli half, y is Bernoulli half. The marginals are both Bernoulli half, but the probability that x is not equal to y is p. Okay, so that is a source that we're looking at, and let us say that we want to achieve the following rate pair. So we want to achieve R1 close to, say, 1. So note that the entropy of x is 1 bit, and let us say R2 needs to be h of y given x. Okay. So clearly, if we had to encode and decode them independently, then h of x is equal to 1 bit, h of y is also equal to 1 bit. What is h of y given x equal to?
H2 of P.
So it's h2 of p. Right. So this is the rate that we want to achieve. Okay. So the way we are going to do it is the following. So what does encoder 1 do? So one way of approaching this problem is to multiply this using the encoder is basically a linear transformation. So encoder 1 multiplies by some matrix H1, some kn by n matrix H1, which needs to be designed suitably. And encoder 2 does something similar. So it multiplies yn by some matrix H2, which is ln by n. All right. This is what the encoder does. The decoder does something a little more complicated, but let's see what the general approach is. Okay, so right now we're operating at this particular. Let's assume that we want to look at this particular rate pair. So R1 is close to 1, R1 is equal to 1, let us say, and R2 equal to H2 of P. Right. So then what would be the dimensions of H1?
One cross n, right?
Recall the definition of the rate.
Okay, kn.
Yes. But what is kn if R1 equal to 1? So asymptotically, what is kn equal to?
N.
Yeah, so it's n, right? So H1 is therefore n by n. All right. And H2 is therefore whatever, n R2 by n, which is n times H2P by n. Okay, so in this case we'll use uh, H1 to be the identity matrix. Okay, that automatically satisfies this property. The rate is equal to 1. So in some sense, we're not doing any compression at all. We're just transmitting the sequence as is. All right. But now, how do we choose H2? So, so really, we can choose H2 to be the parity check matrix of any linear code uh, which achieves the capacity of the BACP. Okay. So if you know what this means, it's fine. If it doesn't, then just don't worry. All that matters is that there exists a linear code which achieves the capacity of the BSC, and this is one matrix which corresponds to that particular code. So so H2 has the property that so basically what the property that we need to use is the following. Uh, so for any, let's say, Zn, which is so if Zn is IID Bernoulli P, then we can recover Zn from H2 Zn with high probability. So basically there is some decoder for which the probability of decoding Zn from Hzn is not equal to Zn. This is vanishing in n. Okay, so let's say this is 1 over n. All right, so this is the property that we'll use, and in fact there exist encoders, so it's possible to construct such Zn's. Sorry, it's possible to construct such matrices H such that you can recover Zn from H times Zn. Okay, and in fact, it turns out that this corresponds to the parity check matrix of any linear code which achieves the capacity of the BSEP. So one set of codes is, for example, the low density parity check codes. These achieve the capacity of the BSC, and as well, and at the same time, you can also have efficient decoding algorithms for such that you can recover H times Zn from sorry, you can recover Zn from H times Zn. Okay, so this is what we need. These are the objects that we need for decompression. So what does a decoder do? What does the Slepian-Wolf decoder do? So the decoder does the following. So what does the decoder have? So the decoder now has access to the two code words, which are basically, it has xn exactly, since we're not compressing xn at all and just sending it directly. We don't have yn exactly, but we have h2 yn. Correct? But now note that yn is not Bernoulli p, right? Xn, so xn and yn separately, they are Bernoulli half. Okay, so uh, so individually, just from h2 times yn alone, it's not possible to recover yn. All right, but we'll see that it's possible to recover both xn and yn. We've already recovered xn, but now we can also recover yn using a basic trick. Okay, and the basic trick is that the BSC can be so one way to look at xn and yn is the following. So you have xn, which is Bernoulli p. You pass this through a BSC and you get yn, right? So through a BSCP to get yn, right? So the BSCP can be viewed as an additive channel. So the addition is now not on the reals but over the binary field. So basically, it's just the bitwise XOR. Where so yn can be viewed as xn XOR with zn, where zn is Bernoulli p. So I'm sorry, I should have said that xn is Bernoulli half. It's not Bernoulli p. Right, so xn is Bernoulli half, zn is Bernoulli p, and the XOR will give you yn, which is also Bernoulli half. Okay. So now we're given xn, we have h2 times yn. So can one of you tell me how you would use this particular claim in order to recover yn? Can you think of one strategy? Yes, any suggestions how we can use these? So first is the whole setup and the encoder and decoder clear? So you have xn, you have h2 times yn.
Sir, am I audible?
Yes. Yes.
So you can write yn as xn plus zn, and you already know xn, and then you
Okay.
have h2 of zn, and then from the above property you can recover it.
Okay, so you have yn, which is equal to xn XOR zn. Okay, I have yn, I know xn. Sorry, I don't have yn, I have h2 yn, which is h2 times xn XOR zn. Okay, so now how will I proceed?
You know xn, right? So you can calculate h2 of xn. And
Okay, so you'll compute
know
h2 of xn. So I know h2 xn, so I can compute h2 yn XOR h2 xn, which will give me h2 yn XOR xn, which is nothing but h2 zn. Okay, so all right, so now
So now, from the above property, you can
Correct.
estimate Zn based on each flow of Zn.
Correct. So now with this, I can estimate Zn. Estimate Zn from H to Zn, and then
Then just you do xn plus
yeah.
x.
All right. So Yn. So call this Zn hat. Let's call this estimate Zn hat. So the estimate of Yn will simply be xn plus Zn hat. Right? Correct. So this is one approach, one way of recovering uh, xn of one way of recovering xn and yn. And note that we are doing better than individually compressing and decompressing xn and yn. So xn has x has entropy 1, y also has entropy 1, and we're in fact achieving a rate of 1 comma h2 of p. All right. So any questions here? So in this case, what is the computational complexity required for encoding? Roughly how many operations are required for encoding each file? In terms of order. So is it order n? Is it order n square, order n cube, or exponential in n?
Order n square.
Yeah, so it's order n square. So basically encoding just corresponds to matrix multiplication. So multiplication of a matrix with a vector, and that can be done in just order n square, just using order n square arithmetic operations. All right. And the decoding complexity really depends on the complexity of this decoder plus some more matrix multiplications. So the decoding complexity is the complexity required for the matrix multiplications plus the complexity of the decoder in the claim. Right? And there are, I mean, at least for certain codes, such as like LDPC codes, you can do this decoding pretty efficiently. You can do it in order n square or even less. In fact, this can be done in time order n times log n or n log square n. Okay. So in fact, it is possible to do this encoding and decoding quite efficiently. You don't have to resort to typical set encoding and typical set decoding. But unfortunately, this works only for specific sources. Right? It doesn't work for all kinds of sources, because after all, we're assuming that you can do this matrix multiplication and so on. So the alphabet has to have a certain algebraic structure in order for you to be able to do all of these linear operations. Okay, and this of course works only for sources like this doubly symmetric binary source. Okay. Any questions?
So currently, like we are operating in a region where there are two sources and only one single decoder, right?
Yes, there are two sources and one decoder, exactly.
And so, like such a result exists when the reverse when only one single source and two decoder, something like that.
Okay, so you're saying that what if we have two different sources and, one
One
source
and two different decoders.
and two different decoders. And the two decoders know nothing, they share no extra information about each other.
Correct, correct, correct.
All right. So then do you think you can do any better than entropy?
So suppose if I can complicate, suppose
Okay.
if each decoder knows some portion of the source message, and
Uh-huh.
suppose uh, uh, and each one wants to decode the whole file, the whole file at the source.
Okay. So there are versions of this known. So for example, one version that has been studied is the following. It's called the multiple descriptions problem. It's more well studied in the lossy compression setting. All right. So you have some particular source. Right. So the problem that you stated can also be set up in the following way. Right. So you have a single file xn. Okay. So each xi could also be sort of pairs of symbols. That's analogous to having two different sources, right? Uh, you have a single encoder. Okay, but the encoder outputs like multiple files, and these need to be decoded separately. Okay, and this guy wants some yn, and this guy wants some zn. So let's maybe call this x1 hat and x1 n hat, x2 n hat. So these are in some sense two different descriptions of this particular source. So one way to think about two different descriptions is, as you mentioned, each xi is let's say ai comma bi, two different symbols. So you have two different files which are correlated with respect to each other. This guy wants one particular file and this guy wants a different file. Okay, that is one setting. But an even more general setting is that suppose that you have a single xn, and you want to, and this person wants to estimate xn with some distortion d1, and the second decoder wants to estimate with some other distortion d2, which may be perhaps less than d1. So he wants a more accurate representation of xn. Okay, so that's one way to think about it, perhaps. Or it could be possible that the first decoder wants to estimate only the AIs, whereas the second decoder wants to estimate both AI and BI. Again, these are general versions. So the so you can operate at rate R1 to the first decoder and rate R2 at the second decoder. All right. So this is one version of the problem, and at least in certain cases this problem is completely solved. But more generally, if you say that these distortions are arbitrary, and then you have arbitrary joint distributions, it's not completely well understood.
So
Sir,
such thing is
this
broadcast channel, right? Like
Yes, but then there's no noise in this channel.
there is no noiseless broadcast.
Correct. So it's the flipped version. Yes. There's another question.
No, I thought like it can come under superposition coding of XN and having two different receivers, something like that.
Two different receivers in some sense, yes. So similar
XN is
ideas are used for
superposition
customers.
coded.
Yes, I mean, so far we've not really seen what a superposition code is yet, but anyway, so in some sense, x1n is xn is the source. X1n can be thought of as a coarse representation of xn, whereas x2n can be thought of as a finer representation of xn.
Okay, okay, sir.
All right,
Yes.
that's one way to think about it, right? Or it's possible that the first decoder wants something else. They don't want exactly this different representations of the source. So there's some part of the source that the decoder one is more interested in, and decoder and the second decoder is interested in a slightly different part. So for example, if xn is basically an comma bn, and decoder 1 is interested in reconstructing only an, and decoder 2 is maybe interested in reconstructing only bn, then again the approach and the rate regions will now change. All right. So again, there are many versions of this multi-terminal source coding problem that have been studied in the literature. Some of them are well understood. Generally, the lossless setting is more well understood than the lossy case. So let me come to that in just another moment. I mean, just in a few minutes, I'll get to the lossy part, and we'll see that, in fact, the lossy case. So maybe let me right away get to it. So even if you have the following setup, right? You have encoder one, the exactly this the framework that we looked at. Okay, but now instead of lossless compression, right? Instead of lossless compression, let us suppose that we want to reconstruct xn and yn with some distortion. Okay, so you xn hat and yn hat. You want to ensure that the expected some distortion between xn xn hat should be less than or equal to d1. The expected distortion between yn and yn hat should be less than or equal to d2. Then for arbitrary sources, this problem is still not solved. There are still many sources for which we don't know what the best achievable rates are. There are inner bounds, there are outer bounds, so there are achievabilities and converses, and at least for certain sources, the achievability and the converse don't match. There is a gap between the best achievability and the best converse. Okay, this is what is called sometimes called the Berger term problem. So we look at lossy compression in a little more detail soon, but this is called the Berger term problem, and even this simple two-source single receiver setting is not completely solved. So you can imagine that more complicated. There are many more complicated scenarios which are still very much unsolved. So one similar problem which is studied is also the following. It's called the CEO problem, which is basically the following. There is a single source, but it is corrupted independently to give yn and zn. So yn is some corrupted version of xn, zn is some corrupted version of xn. So you can think of you can assume that yn is obtained by passing xn through some DMC, zn is obtained by passing xn through some other DMC, and yn is given to encoder 1, Zn is given to encoder 2, and this is each of them are yn and zn are sort of compressed or encoded, and this is given to a decoder. And the goal of the decoder now is not to estimate yn and zn, it's to estimate xn. Right? So the goal is to estimate xn given some compressed versions of yn and zn. Okay, so again, this problem has been extensively studied, uh, and at least in many cases the CO problem is solved, particularly for Gaussian sources. But again, the general CO problem is also open. Okay, so there are many such versions which are still unsolved. We don't know. We again have inner bounds and outer bounds. Ultimately, most inner bounds make use of these ideas from of typicality. They're all generally joint typical. They use some sort of joint typicality encoding and decoding, and and converses typically involve Fanos inequality in some form or the other, but probably we need completely different approaches in order to solve all of these problems completely. All right. So this was just some extra information. There are many such multi-terminal problems that have been studied, and each of these arise from certain practical applications. Right. So once again, if you think about the sort of distributed sensors problem, it could be that you have some particular parameter that you're really interested in estimating. These are measured by two different devices, and they could have measurements. There is some noise in measurements, and these measurements are transmitted to some central server or a fusion center, whatever, and the goal of the fusion center or the server is to estimate the actual parameter. All right, and so what is the best that you can do? But note that we're all operating under certain rate constraints, right? You cannot send yn exactly to the fusion center or to the server. All you can do is transmit some compressed version. So one can always ask, okay, what is the best you can do under certain rate constraints, or for a given, or another way of looking at it is given that the estimate has to satisfy a certain expected distortion constraint, or you want that xn hat should be as close to xn as possible. What is the minimum rates at which you need to of communication over here? What is the minimum number of bits that need to be transmitted in order to perform this estimation as well as possible, right? Okay, so any questions? So as I said, there are many such multi-terminal problems. It's not possible to cover all of them in class. The El Gamal and Kim textbook has a very comprehensive treatment of many of these various source coding and channel coding problems. But I guess the Slepian-Wolf problem is sort of the most basic, and it gives you a flavor of what kind of techniques are used. So since it's impossible to cover all of these problems in class, it's just that I give you a flavor of what is out there. And if you're interested in a particular problem, you can look up the textbook, or we can also discuss it offline. Okay, so this is about the two-user source coding problem. We can generalize this to k users. So you have, let's say, x1n, x2n, up to xkn, and these are jointly distributed. So according to some joint distribution P x1, x2, xk. All right, and the components of each vector are all IID. These need to be compressed separately. So you have encoder 1. So x1 is given to encoder 1, x2 is given to encoder 2, and so on. And the goal is to design these encoders but all of these need to be jointly decoded. And the goal of the decoder, so again we're looking at the fixed length vanishingly small probability of error setting. The goal is to get x1 hat, x1 n, n, and we want to know what is the best rate tuple that can be achieved. All right. So we say that a particular rate tuple is achievable if it's possible to construct if we can construct encoders and decoders or sequences of encoders and decoders such that whatever each encoder I has a rate approaching Ri, and the probability of error, which is the probability that x1 n hat, xk n hat, so the probability that all of them are decoded correctly tends to 1, or the probability that any of them is decoded incorrectly tends to 0 as n tends to infinity. Okay, and we want to know what is the best rate pair that is achievable. In fact, the optimal rate region for this particular problem, for the general K user problem, is well understood, and it follows exactly as the proof is essentially identical to what we did for the 2-user case. It is just that you need to use the conditional typicality lemma and the joint typicality lemma a little more carefully. You just have multiple sources instead of just 2 sources. The optimal rate region is the following. So for general K users, it is the intersection of all these rate regions. So it is a set of all, which it is the R1 through Rk that satisfy all of these properties. So each Ri should be greater than or equal to h of xi, Ri plus Rj should be greater than or equal to h of xi xj, and so on. So for every, sorry, so each Ri should be greater than or equal to h of xi given x1 through xi minus 1, xi plus 1. So Ri should be greater than or equal to h of xi conditioned on all the other xj's. Ri plus Rj should be greater than or equal to hi xj conditioned on all the other xl's not equal to I comma j, and so on. So for all subsets S up to K, the summation overall Ri, where I belongs to S, should be greater than or equal to h of xs, which is given xs complement. So this is basically set of all xi, where I belongs to S, and this is set of all xj, where j belongs to S complement. Alright, so this turns out to be the optimal rate region, and this is very well understood. Again, we can achieve all of this using joint typicality encoders and decoders. Alright, sorry, random encoders and joint typicality decoders. All right. Any questions?
So will there be an upper cap on k, or like for any given k we'll be able to find the decoder to achieve this?
So the assumption is k is fixed. It's some constant, no matter how large it is. But k does not depend on n in any form.
Okay, like then for any given k, like for any large number of users, we'll be able to find a decoder so to achieve this.
Yes.
Okay.
But generally, the assumption is that n is much larger than k. That is important.
Okay. Okay. Yes, sir.
Right? So you fix a k. It doesn't matter whether k is 100, whether it is 1,000 or 10,000. But but the assumption is that you fix k and then you let n to tend to infinity. Right?
Yes,
Because
sir.
there are many problems in multi-user information theory. Particularly, these are of interest more recently, but related to communication problems rather than compression problems, where you have a very large number of users, and the number of users also scales with n. Right? So you have short packet communication, but involving a very large number of users. So now the number of users is roughly the same as the length of the packet that each user is allowed to transmit. And in that case, the whole problem changes. So now things are not that well understood anymore. But in the scenario where you have k users and n, the size of each packet or the size of each transmission is much larger than k, things are much better understood.
Yes, sir. So you mean in the finite block length regime, which they say, so that way.
It's a little more involved than just the finite block length regime, because that is something slightly different. So the
Okay.
finite block length regime is where again k is small, n is much larger than k, but n is still finite. So you don't look at just the
Okay.
asymptotics, but for each n and for a fixed probability of error, what is the best you can do?
Yes, sir.
All right. So there is this whatever massive access communication or massive random access and similar problems, where you can have, where again you may be interested in the asymptotics in the asymptotic n regime, but where k maybe scales as square root of n, or k scales as log n. Right? So both k and n simultaneously tend to infinity in a certain way. Right? So that is one class of problems that people study. Uh, but of course, you can also talk about the case where k is finite and n is finite, and for a fixed k and n, what is the best that you can do? Right? So these two are kind of related problems, but they're still different, and the techniques used for each of these are different.
Yes, sir. I get it. Yes, sir.
Yeah, but classically, what people study is where k is it could be large, but it's fixed. It's a constant in terms of n, but you let n to tend to infinity, and that is what we have a much better handle on, and that is what these typicality and other tools help us analyze. Right? So typically, when you look at uh, finite block length results, the approaches used are slightly different. In fact, so as it was alluded to like earlier, the typicality decoder is not optimal. Right? So the optimal decoder in any setting is always the maximum likelihood decoder. But studying the maximum likelihood decoder is a lot more complicated. And I mean, but people have already studied it. It is just that it is for at least the point-to-point case, it's easier. But for general multi-user settings, analyzing the map decoder or the ML decoder can get very very hard. Right? So if you want to see an analysis of uh, the map decoder, map decoding for just the channel coding problem for DMCs, single user case, or the point-to-point setting, you can take a look at the textbook by Robert Gallagher. I think it's called Information Theory and Reliable Communication. It's again another classic book. Robert Gallagher was the inventor of the LDPC codes, which are currently used in many of the standards. Right, and this book really has a full analysis of the map decoding for communication over discrete memoryless channels. In fact, so in this book, the channel coding theorem is derived, or the achievability part of the channel coding theorem is derived using by using an analysis of the map or whatever ML decoder. So you can, if you're interested, you should take a look at this particular book. I don't remember which chapter it is in. I think chapter 4 or 5 or something like that. All right.
Sure, sir.
Any other questions? Okay, so let's stop at this point. So in the next class, I'll do a brief discussion about lossy compression. Again, in the interest of time, I will not get into this in too much detail, but at the same time, I want to highlight the differences between lossy and lossless compressions, and 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 sort of discuss the connections between lossy compression and channel coding. It turns out that the two are related in some form. Both correspond to certain geometric problems. One turns out to be so the channel coding problem turns out to be a problem of packing, whereas the lossy compression problem turns out to be a problem of sort of covering. And we'll see that see this interpretation in the next class. But maybe we'll just sort of try to wrap up lossy compression in one class, and then we'll want to move on to multiple access channels and then to broadcast channels. All right. Okay, so if there are no further questions, then let's meet next week. See you then.